The objective of this video is to introduce cascaded bridge converters and analysis tools for high-frequency rectifiers. We've previously been talking about flyback and forward converters where the transformer is integrated right into the single-pole double-throw switch. Now we're going to talk about a different philosophy for DCDC conversion, for isolated DCDC converters, which is the cascaded structure that I've shown below in block diagrams. So in this structure, every step of the energy conversion process takes place in a distinct stage. You can see on the left side we start with a DC voltage. This might be a rectified DC voltage from the wall. It might be the DC voltage of a electric vehicle battery. But the point is that it's DC and it comes from somewhere. The DC voltage is connected to a voltage stiffener for an inverter, so a capacitor, and the capacitor is then directly connected to an inverter. And again, remember, these are distinct blocks, so the inverter is its own distinct block in the system. The inverter is connected directly to a transformer that steps a high frequency AC signal up or down to a second AC signal, which is then rectified. And finally, that rectifier is connected to a capacitor, which filters out any ripple components so that you're left with a DC output voltage. So we're going to be talking about these systems where the inverter stage is implemented as a full bridge or half bridge converter. So let's sketch the circuit schematic for each converter. And the full bridge converter you should be pretty familiar with by now. The half bridge is going to be familiar, but we're going to show how you can use this as a bidirectional inverter, which is a little bit different than how we talked about it previously. So the full bridge converter is drawn on the left, which again should be familiar to you. And we've commented before how this quantity that we've attached in the center here can be either a source or a load. And the quantity that we've drawn in the center and circled in orange is, in our case, the transformer stage of our cascaded DC-DC converter. So this stage can be a source or a load depending on the direction of power flow. If the transformer is acting like a source, then this is called a full bridge rectifier. If the transformer is acting as a load, this is called a full bridge inverter. We can also draw a half bridge inverter and a rectifier, which we'll now do on the right side. In both converters, our transformer, or our source and load, are connected in the same location. But the key difference is that in the half-bridge converter, we have placed a voltage balancing network on the right side. We've placed a voltage divider network on the right side of the converter. And this network consists of resistors and capacitors. These resistors and capacitors take the place of the active devices we have in our full-bridge converter on the right side. So, since in our application we're going to be driving a transformer, which implies that our currents are going to be AC, we're able to implement this passive voltage divider network using capacitors. And in theory, we wouldn't need the resistors at all. The capacitor should maintain, it should be a passive voltage divider. So if we have a 100-volt bus and we put two equal capacitors, we should end up with 50 volts across each capacitor. So let's say that we had a 100-volt bus. We should end up with plus 50 volts here and plus minus 50 volts here. In reality, capacitance values will be different. For some reason or other, the voltage might start to deviate. So we put resistors in parallel with the capacitors to reinforce the voltage balancing. So under DC conditions, the capacitors appear as an open circuit. So if you had some kind of DC offset in the current waveform, you would end up having your voltage no longer have this 50-50 split. And so the resistors help compensate for that. And so similar to how in this converter on the left side, the full bridge converter, we're able to control the left and right duty ratios independently in order to get left and right pole voltages that are independent. So for example, if we have a duty ratio on the left side equal to 75%, then we're going to get a pole voltage of 75 volts. And if on the right side our duty ratio is 25%, we get a pole voltage of 25 volts, which would give us a total output voltage of 50 volts. Whereas if on the left side we had a duty ratio of 25%, we get 25 volts. And the right duty ratio of 75%, we get 75 volts, which would give us an output voltage of negative 50 volts. And we've written this on the screen a few times in different forms, showing that we're able to get bidirectional voltages with the full bridge converter. We can do a similar thing with a half bridge converter, where we note that this node on the right side here is now permanently fixed at the value determined by our voltage divider. In this example case here, it's permanently fixed at 50 volts, or so we assume it is permanently fixed. As long as we did a good job with designing our passive voltage divider network, we can treat that as a fixed voltage of 50 volts. So if on the left side we set our duty ratio equal to 75%, we'll end up with a pole voltage on the left side of 75 volts. And our output voltage is going to be our pole voltage minus the voltage of our passive voltage divider. So it's going to be 75 volts minus 50 volts, which gives us an output voltage of 25 volts. So we can make our first interesting observation here, which is that for the same throw voltage and the same duty ratio, we get an output voltage which is half the value of the full bridge converter. So the full bridge converter had an output voltage of 50 volts, the half bridge converter has an output voltage of 25 volts. Now if we apply duty ratio of 25%, we get an output voltage of 25 volts minus 50 volts, which is equal to negative 25 volts. So you can see that we've preserved our ability to create a bidirectional voltage, so it's still an inverter, but now we've limited ourselves to having half of the voltage output rating as a full bridge converter has. And this makes sense. There's no such thing as a free lunch. We've made our circuit less expensive by limiting the active devices of the second throw, but we've also limited the output voltage range that we can achieve across our source or our load. In practice, you have to be very careful about voltage and flux balancing with this converter. You need to make sure that, well, for one thing, you need to make sure that this voltage here does not walk off to some undesired value. But when you're connecting a transformer here, you also need to make sure that you don't end up applying some kind of average voltage to the transformer, since the transformer core flux changes with the voltage that's applied across it. So since V is equal to dφ/dt, the flux in the transformer is the integral of your voltage. This is Faraday's law. You need to make sure that your voltage has an average of 0 volts, or you'll end up causing your transformer to saturate. And related to this, we can note that we only see the half-bridge converter for relatively lower power ratings, where the cost advantage of removing those active devices is very significant. For higher power ratings, we become more sensitive to issues like voltage and flux balancing, and so we want to have very precise control of the voltage waveform we're applying to our transformer. And so there, in the higher power ratings, you tend to see the full bridge converter instead of the half bridge converter. So an approximate rule of thumb for this is that below about 500 watts you see half bridge converters, and above about 500 watts you see full bridge converters. And so you can start to get a sense of the power ratings at which you see all of the converters we've been talking about. When we introduced the flyback converter, we noticed that we really only see it in applications in the 0 to 50 watt range, or approximately. These are all approximate things. In the forward converter, we talked about it being used up to around a kilowatt, and here in the full bridge converter, we're now talking about higher power ratings yet. They can go up to many kilowatts. Okay, so we've sketched the two topologies of the bridge converter that are used in cascaded DC-DC converters. Let's now sketch what a full converter looks like. So we've indicated our block diagram up here. Now I'm going to sketch an actual circuit schematic for this complete converter. So in the schematic here, we've got we've got an implementation of each of these stages. And moving left to right, we start out by noticing that we have our capacitor stage. And then we've got a full bridge converter. We have a transformer. We'll assume it's a step-up transformer. We have our rectifier. And finally, we have a capacitor again. And so if we go from left to right and we note down what is DC and AC, you see that we start with DC, and the output of our inverter is high frequency AC. The output of our transformer is AC at the same frequency but stepped up. And then the output of our rectifier is DC, which is further filtered on our capacitor. Each of these blocks could take on different forms. For example, the full bridge block, we could have implemented this as the half bridge. If we had power flow going this way instead of the other way, if we had power flow going right to left, this could have been a full bridge rectifier or a passive rectifier, a half bridge rectifier or a passive half bridge rectifier. Moving to the right, our transformer could have been a step down transformer. It could have had a 1-to-1 turns ratio. And then our rectifier, while we've sketched this as a full wave rectifier or a full bridge rectifier, we've sketched it as a passive full bridge rectifier. We could have made this an active rectifier. We could have had it be a half bridge rectifier. So you can see that there's many different options for how you implement this circuit. And the way the method that you choose to implement it depends on the conditions of your application, whether you need bidirectional power flow, whether you have a certain ripple voltage or ripple current target. It also depends on your experience and your expertise. So if you're working for a company that is an expert in developing half-bridge inverters and half-bridge rectifiers, they're not going to think twice. They're just going to implement this as a half-bridge system. So the point here is that what we're discussing now is one particular form of this system, but there are many possible circuit schematics that comply with this general cascaded DCDC converter structure. Let's now sketch the equivalent circuit of this system. Our left side to the bridge inverter can be summarized as being a square voltage wave source, and then attached to the equivalent circuit of a transformer. Notice that in the equivalent circuit of the transformer, I'm including the series leakage inductance on the secondary. This will become important in a little bit. So we now have the equivalent circuit of our system that we can study to investigate the transient behavior in the operational waveforms. The second portion, or the second objective of this video, is to introduce high-frequency analysis concepts. So we're going to work with this equivalent circuit, but study the rectifier portion of it as a high-frequency rectifier. So at the beginning of our class, we talked about single-phase low-frequency rectifiers, single-phase low-frequency and low power, so 60 Hz rectifiers, and they were all around the range of these 20 volt ampere transformers that you can purchase from DigiKey. Now we're talking about single-phase rectifiers, but they're going to be higher power and much higher frequency. They might be 100 kilohertz, 200 kilohertz, it might be 1 kVA, 2 kVA, so orders of magnitude higher frequency and higher power, and this changes the assumptions we make when we construct our more simple equivalent circuit models to derive the operating principles. So the first key difference is this increase in frequency. And at the beginning of the class, with our 60 Hz transformers, we said, well, the frequency is pretty low, and so therefore any impedance that we would see from the leakage inductance of the transformer does not matter. We can consider it negligible. That's no longer true in this case. So if we're switching at 100 kilohertz, if our switching frequency of our bridge converter is 100 kilohertz, suddenly the impedance created by a leakage inductance excited at 100 kilohertz becomes very sizable. These transformers are operated at much higher power levels, and so this means that when we design the transformer, we're doing everything we can to reduce the losses. Since we've increased the frequency, we've decreased the size of the transformer, the physical size. Based on our area product analysis, we know that the size should scale by 1 over the frequency. So by increasing the frequency, we've decreased the size, and that means that when we increase our power, we have a much higher power density for our transformer, so any losses that we have in the transformer become particularly problematic from a thermal perspective. If you have a higher loss density, even if the total losses are not that great, but the density of the losses is great, it's hard to get the heat out. And so therefore we do everything we can to reduce the losses, and that includes making our coil resistance very, very low. In the low frequency transformers, we would actually increase our coil resistance as a means to prevent short circuit currents. In this case, we're doing everything we can to eliminate or greatly minimize the resistance we see in our coil winding, which means that in our equivalent circuit model, we can typically actually neglect the series resistance of the coil. And the final difference is that we're typically working at higher voltage levels on the output of our rectifier. In a lot of cases, we might be working at the kilovolt scale. And so when that is true, and that isn't always true, but when that is true, we can neglect the voltage drop across our diodes. Because remember when we were constructing our DC equivalent voltage at the beginning of the semester, we considered it to be 2 times the diode voltage drop plus our output voltage. Well, if the diode voltage drop is on the order of a volt and the output voltage is on the order of a kilovolt, the 1 volt diode drop simply does not matter. It does not affect any of the analysis. So that means we can oftentimes ignore that voltage drop from our analysis, in our analysis. So let's now redraw this equivalent circuit here, but only including components that are necessary to study the rectifier operation. That is, we're going to replace all of this by an effective voltage source right here. And this is the same as we did in the beginning of the semester, only now we're going to be implementing these changes. So you can see that we've labeled our source voltage right here as being a square waveform, and this is due to the pulse width modulation that is occurring within the bridge converter. That is, our bridge converter's output voltage, the voltage applied to the primary of the transformer, is always either at the throw voltage of the bridge converter or the negative throw voltage of the bridge converter. You've got this square waveform. Next, in place of drawing a resistor, we've labeled our leakage inductance of our transformer. We've indicated that our output voltage source is, now a voltage source, so we're modeling our capacitor as a voltage source. So again, this is all reminiscent of what we did at the beginning of the semester. And we can determine, we can further simplify this for the time when our diodes are conducting as the following equivalent circuit, which is also the same as what we did at the beginning of the semester. Only we're replacing our series resistance with a series inductance, the leakage inductance. So I encourage you to go back and look at your notes from the 3rd lecture or the 4th lecture of class when we talked about the design of the low frequency rectifier. You'll see these same equivalent circuits, but with the modifications that I've described here for the high frequency, high power case. Next, we can draw the transient waveforms for our voltage and our current to locate the inception and extinction time of the currents. So in the beginning of the class, we did the same type of exercise, but with 60 Hz sinusoidal quantities. Now we're looking at high frequency square waves as our excitation. So we use this type of plot at the beginning of the class to determine when our current would turn on and off. And we had noted that when Vs goes above our VDC equivalent, our current will start to flow through one of our diodes. So at this instant of time right here, a current will begin flowing, and it will continue flowing until Vs decreases below VDCE. So that was our observation at the beginning of the class, And in fact, at that point, we would have said that this current would be proportional to Vs minus VDCE, because all we had in this equivalent circuit right here was a resistor. But now we have an inductor. And so we can note from this waveform that our inductor voltage, VL, is going to be the difference between Vs and VDCE. So if this brown trace is our inductor current in this region is going to have the derivative of V is equal to L di dt, so therefore di dt is equal to V over L. And that's the slope of the line in this quadrant. Finally, when we get to the end of this region, where our source voltage goes to 0 volts, it goes below the DC equivalent voltage of our rectifier. At the beginning of the semester, we would have said that the diodes all turn off at this point. However, that is no longer possible because we have this leakage inductance that's in series with the rectifier. So we need to allow some time for the current to decay. And this current is going to decay at a rate determined by the voltage applied across it, which during this region, right here, VL is going to be equal to a negative of VDCE, which gives us the following derivative for our inductor current. So on the final exam or on a homework assignment, I should be able to ask you to make simple calculations like this for the extinction time and the inception time. So remember, extinction time is when our current turns off, so this would be T extinction, and inception time is when the current turns on, based on waveforms that I provide for you. So this is not very complicated analysis. This is just the simple differential equation for current and voltage across an inductor. And you should be able to conduct nearly qualitative analysis like this to determine the basic behavior of your high-frequency rectifier. And so we can note here that this whole pattern repeats itself twice. So if this is time Ts by 2, we're going to quickly have the same voltage waveform appear out here, but because we have a full wave converter, a full wave rectifier, we would see it reflected up to the positive y-axis when we're analyzing it via this circuit. Finally, I want to point out that the way we regulate the output voltage of this converter is by changing the duty ratio of our Vs voltage waveform. And remember, Vs is the output voltage of our transformer, which is determined by the voltage we apply on the transformer primary by using our bridge converter. So by changing the duty ratio of our bridge converter, we are able to change the output voltage of our cascaded DCDC converter. So in summary, this video has introduced the cascaded bridge converter structure as well as analysis tools to study high-frequency rectifiers. We've commented that the cascaded DC-DC converter structure is fundamentally different from the flyback and forward converters that we've talked about previously because it has distinct stages for each step of the DC-DC conversion process. We've reviewed how the full bridge converter works, and we've detailed how the half-bridge inverter/rectifier works by having a passive voltage divider stage in place of an active single-pole double-throw converter. We then sketched a circuit realization of the cascaded DC-DC converter, and we've commented how each stage can be replaced by alternate circuit topologies based on price, based on the requirements of the application. And finally, we've developed analysis tools to study high-frequency rectifiers, similar to how we studied low-frequency rectifiers. We noted the key differences that we had to make, or the key changes we had to make, in order to use the same analysis framework that we developed at the beginning of the semester. And then we worked through what that analysis looks like.